Alice, Bob, and Eve explain Shor's algorithm.
I can't remember the combination for the lock on my bike. I've been trying different combinations for hours. There must be thousands of possibilities.
That reminds me of factoring large numbers. It's easy to multiply two prime numbers together, but incredibly difficult to work backward.
That's exactly what Shor's algorithm in quantum computing addresses. It can factor large numbers exponentially faster than any known classical algorithm.
How does a quantum algorithm help with factoring numbers?
Think of your combination lock. Classically, you'd have to try combinations one by one. But Shor's algorithm is like having a special key that reveals patterns in the lock's mechanism.
Let me show you with this small pendulum. Imagine each possible factor as a pendulum swinging at a different rate.
Like different frequencies?
Exactly. Shor's algorithm first converts the factoring problem into finding the period of a function, like finding how long it takes for a specific pendulum to return to its starting position.
Classical computers struggle with finding these periods efficiently. But quantum computers can use something called quantum Fourier transform to find periods almost instantly.
The Fourier transform. Isn't that related to frequencies?
Yes. It transforms information from the time domain to the frequency domain. The quantum version can analyze all possible frequencies simultaneously through superposition.
It's like setting all possible pendulums swinging at once, and then the quantum interference pattern reveals which one matches our problem.
Then once we find this period, there's a clever mathematical relationship that gives us a good chance of finding the factors of our original number.
So instead of trying every combination, Shor's algorithm finds a hidden pattern that reveals the answer?
Precisely, and that's why it's so revolutionary. Problems that would take classical computers longer than the age of the universe can potentially be solved in minutes.
Which is also why it has significant implications for cryptography. Many encryption systems rely on the difficulty of factoring large numbers.
So this combination lock would be secure only until someone comes along with a quantum computer running Shor's algorithm?
Yes, that's why researchers are developing quantum-resistant cryptography, new locks that would be secure even against quantum keys.
Though it's worth noting that we still need much larger, more stable quantum computers before Shor's algorithm can factor numbers big enough to break real-world encryption.
So quantum computing doesn't just solve problems faster, it can solve them in fundamentally different ways. Oh, and I think I remember my lock combination now.